the head of research for CNRS, which is the climate organization in France, right? And his background is a PhD in physics from Hamburg University in Germany on extreme value analysis in geophysics. So because of that, he has interest in nonlinear dynamics, which is not the standard extreme value story that you get from most people, dynamical systems and climate, and also finance, right? And one of the fun things that I saw that he's doing, which actually goes beyond that, which matches up with one of the things I'm interested in, is agrivoltaics, which is not going to be talked about today.
No.
But the interesting thing about a lot of his work is that he's been looking at extreme climate events and their attribution. Where do these guys come from? Are they really unusual? Can we ascribe them to possible historical states of nature, or are the states of nature changing? And it fits with this idea that from a theoretical perspective, how do we understand these changes rather than simply looking at numerical model output and saying, hey, I've not seen this before. So that's the framing for his talk. And we're very pleased to have him here. He was just mentioning that the climate impact of his trip is probably significant, so we should make sure that it's valuable to all of us. So I hope that you guys will all keep that in mind and we have a good discussion. With that, David, all yours.
Thank you very much. Thank you for inviting me and having me here. So yeah, it's a great pleasure to be here after this long trip from the other, well, it's transatlantic, but also transcontinental trip, right? Because it's almost on the other side of the American continent. And well, Upmano, you made a very nice introduction. So today I will try to get you through the understanding of how we can use dynamical system theory to really make actual statements about attribution of extreme events, right? So it's a long format, this talk also for me, because I guess that we have 90 minutes together. So feel free to interrupt me any times. Feel free to stand up, grab food, and yeah, let's make this very informal, please. And let's try to get all together towards the understanding of what I'm saying. And yeah, so you see here that there is some logo. The CNRS is the French National Center for Scientific Research. So Upmano is a bit more general than just climate. Me, I'm in the climate division, let's say. So I'm a civil servant in France. So I represent the French state when I do research. And the interest of France and the interest of all of us is to build a future that is more resilient to the climate change and that has some understanding on how the extreme events that happens in the climate system are affecting our societies and what we can do to prepare our society better and to understand where they come from. So, but before getting to this point, I want to start with a cartoon that you probably know, but that I will try to explain from the point of view of a physicist, right? So the first thing that I say also when I talk to the media or to the general public about the climate system is that to understand the climate of a given location, we cannot just rely on meteorological observation, right? Because when we know the meteorology, and we observe the conditions in Paris, for example, in summer, they could look like the condition in Arizona in October. But if I just observe this for a few days, I cannot get a clue of how the climate is in Paris, right? So the climate doesn't answer to the questions what I wear tomorrow. It answers to the questions what I will build as infrastructure or as house, for example, housing in a given country, right? So to answer to this question, I have to observe many different things that are not just related to the atmosphere, but are related to 4 other spheres that are not spheric, okay? But you know, physicists, we like to define things that are spherics that are not, like cows or other things like this. So the spheres in the climate system are the hydrosphere, the atmosphere. So the hydrosphere is everything that is iced, for example, the oceans, but not only the rivers, the lakes. Then the cryosphere, everything that is iced. And then we have, of course, the biosphere and the lithosphere, everything that is solid, right? So the questions for you now is, what is different with this, within these different spheres that are not spheres? Do you have any clue? So the things that I'm saying as a physicist, even to the general public, is that they are characterized by different properties. Like, let's think to these spheres are different materials, right? So atmosphere is air, the hydrosphere is water, the lithosphere is solid. So the difference that they have, for example, some journalists last week answered like density, right? Huh? I would say like viscosity from a more physicist point of view. So viscosity of the air is very volatile. It's a bit like finance, right? So the motion, the things that happen in the air are very fast compared to the water or compared to what happens in the ice or in the ground. And that's, in fact, it's what makes the complexity and the beauty of all the system, right? Is that we have different components in interactions. When I say components, I'm talking about material, the spheres, and so on, and that these have different properties. And these different properties correspond to different time and spatial scales in the movement of this object. So the air, we say that is very volatile, and so if we look at the time of a storm at mid-latitude, it's typically of the order of days, right? 2 or 3 days. If we look at the motions of a particle in the ocean, that's much longer. It takes thousands of years to make a round trip in the ocean for a particle of water, right? And if we look at ice, dynamics is even longer. And for the continent, well, we just assume that they don't move, but in fact they do. So if you look at the climate on millions of time scale, is even different, right? So, but why is this interesting? Because if I now put energy in this system as an external source and I put the sun, right? And I look what happens in the climate system, so inside here, well, I get that I have fluxes of energy. Why? Because the Earth receives the sunlight more at the tropics than in the polar regions. And I can tell you, coming from slightly higher latitudes, that there is a huge difference between the climate in Paris and the climate in Arizona. But then in physics, we don't like things that are not at equilibrium, right? And so we try to redistribute the heat within the climate system, and everything that happens in the atmosphere, in the ocean, it's the fluxes, the currents that we have, the storms, the weather phenomena are just things that the climate system uses to redistribute the heat, right? So they're not there for us. Let's put it from the point of view of this cartoon. They are there because the climate system is not at equilibrium. Never. There is always this difference between the equators and the poles, and we have to redistribute the energy, okay? So these are the very basic considerations, but you will see that they will be useful for us in the next slides to understand what we can do and what we cannot do with this system when we try to think at it as a dynamical system, right? And so, in fact, it's hopeless to describe just as a whole this system when we want to understand futures on it. Of course, we can run huge experiments that are the experiments of the global circulation models that try to get at once all the spheres, all the components of the climate system, and have a simulation that can reproduce the dynamics of the air system. This is what we do in the IPCC, and it's very useful, for example, to understand that the CO2 emissions are making the temperature higher, and that we have a climate change, and how this climate change can affect the different components of the climate system. But when we want to go more in details to understanding the dynamics of a single storm or a single phenomenon within the climate system, we have to focus on a specific problem, right? So we cannot address all it at once, but if we want really to understand, we have to simplify the problems and try to build conceptual models that will allow us to understand what is going on. And just by looking at the dynamics of a general circulation models will not necessarily help with this, because we will miss the important things. We will not be able to tell a story, to link what is really happening with few elements. That is exactly the goal of dynamical system theory, right? So general circulation models are huge dynamical systems, or are systems of equations that can be iterated in a computer to produce a dynamics, but they don't tell us a story. So how we tell a story about the weather extreme events that we have understood from the previous slide, that are those who are carrying the energy from different states of the climate of the system. And here what I'm showing you is just what you see. For example, if you turn on the TV and you look at the weather channel, right? This is what we will see in Europe for some animation of the weather at daily scale. Here the time is flowing for each frame by 6 hours. And I'm focusing on a region that is roughly the North Atlantic. So here it's Canada and here it's Europe. I could have taken a region similar, centered over the US. That's, since I will talk a lot about the climate, what's happening here in this region, I'm taking this. And what you can see is that focusing on this region and looking at two specific variables that are the sea level pressures in isolines, okay, and the geopotential height at 500 millibars, we can get some idea on how is the weather, okay? And I will explain you what I mean by this. First of all, let's look at pressure, okay? So pressure can be high and can be low. When the pressure is high, like here, what we expect is to have stable weather, okay, and basically the absence of weather phenomena. We can look outside. We should have high pressure, right? So, and when we have low pressure, for example here, well, here we expect to have extratropical cyclones, so storms. And this brings rain. Usually they bring advection of warm air, okay, along in an anti-clockwise direction in our hemisphere north. And so just looking at these two, at the sea level pressure, I'm able to make a sort of weather forecast, or to say, using the law of physics, where it will rain or where the weather will be stable, okay? So this is how our colleagues were doing the weather forecast in the 80s and in the 70s. They were taking the pressure, or the other things, that is the geopotential height. Do you know what is geopotential height? If you don't know, well, it's simply, instead of fixing a level, okay, in terms of height, for example, 5,000 meters, we look at what is the height in meters, where the pressure is 500 millibars, hectopascal, okay? So and this can vary of about between 4,900 meters to 6,000 meters, okay? So again, it's a tracer of the atmospheric circulation, and basically give us an information that is complementary to what the pressure gives us, but it's not exactly the same. But what I want to show you here is that it's what you know, it's common sense for the moment. From the weather forecast, you know, if you are trained in meteorology, that here it's good weather, windy from the south, warm advection. Here you start to have some rain, okay? Then the cyclones come in, you have more rain. And then when the cyclone will be over, you will have good weather again. It's kind of things that, so can we use this to understand something about the dynamics? Can we use to answer the question, is this map that I'm observing a recurrent map, something that I expect to see every day, right? Or is some kind of extremes? How likely is that I have this cyclone here or not, okay? So that's the kind of questions we will try to understand during this talk. So you see from the general problem of the climate, I could have taken chemistry, I could have taken hydrology, right? I'm taking this one. And this means that I don't pretend that I will answer all the other problems, but I will focus on these questions on if I have a cyclone, and if, for example, it rains in Portugal, right? What is, how extreme is this, the fact that I'm having a cyclone? And how frequent is this? I have to expect it, how persistent it is. And I will show you that I can answer this in the framework of dynamical system theory. So the first things that I will use is the idea that although we have every day a different weather, that it's not always the case. I mean, if you're in the desert, it's a bit difficult to explain. But if we look at the large scale, right, every maps that I've shown, it's different from a maps that I've previously analyzed, thanks to chaos theory. So I never have two identical recurrences of the weather because it's a chaotic system. But I can find analogues, right? So I show you here 2 days that are separated in time, where we had snow in Rome. And you see this is St. Peter's Square, where there is a Pope. And the Pope couldn't celebrate the Mass because it was snowing. So people were going skiing instead of praying. Okay, so that's basically was in the 4th of February 2012, and this is in 1956, right? So if I look now at the kind of map that I showed you before, so pressure, again, is in isoline, and the colors is the geopotential height. These two maps are separated in time, but they show a similar structure. It's not identical, but it is similar, okay? So what we say and what I will use in this talk is that they are analogues, okay? They are weather analogues. The concept of weather analogues was born in Germany, and they were called Grosswetterlage, so patterns that resemble each other somehow. And of course, this is something that doesn't come from meteorology. It took a very long time to understand that this concept of analogues was existing in the weather. It's even like Lorentz that realized this. Perhaps, but is a concept that is known in astronomy since the Assyrian, right? Because they were observing the stars and they were seeing that in the season and the position of the planet, and they were seeing that there were recurrences of pattern where the planets were going from constellations and so on and so forth. So this concept that things can come back and be recurrent is what we have used since the beginning of time to do what? Learning. And in fact, the idea of recurrences is the idea that is as the basis of every machine learning algorithm, is what we are feeding the artificial intelligence. We are putting this idea of learning, that is the learning of all humanity, in a dynamical system fashion, I would say, in a machine. And so that now the machine can learn and produce things the way, more or less, we are doing. Okay? So that's, I find it fascinating. But in the weather, to go back, the idea is that things do not repeat with respect to astronomy. And if there are astronomers or astrophysicists here, please bear with me. I know also the chaotic, there is a chaotic behavior in the solar system, but at a short scale, we have the feeling that the motion of the planets are periodic, right? For the weather, no. So we can wait several years to observe again snow in Rome, but then, for example, after 2012, we had snow again in few years, right? So the recurrence time is not deterministic. Okay, we can think of it as a sort of a stochastic variable, but it's not random, right? It's the law that governs the climate system there are still law, okay? So there is a mixture between randomness and the fact that there is a chaotic system underlying, and this is what makes this structure exist and being recognizable, but so they're not random, but at a certain point, the recurrence is not exact. So let's see how we use this. So now I go back to, again, the Lorentz 1963 system that you know. If you don't know, this system is a system of 3 equations, x, y, z. And these 3 equations you can write on the whiteboard, and then you can write 3 lines of code to simulate this system. And now it will run on this. So you can really have an idea of what is chaos just by using your smartphone. And the idea is that if you start from a state that is this initial condition here, right? This is you have free value, x, y, z. You give this to your equations, then you iterate, and then you can see with a certain delta t, small time interval, where your system is. And what I did in this simulation is that I colored with time the position of the point x, y, z. And for those of you that don't know chaos, that's what a chaotic attractor looks like, okay? So I'm saying chaotic and attractor. Attractor is the most the easiest things to understand. You start from here, right? And then after a certain time, you fall on an object, okay? So the idea is that you can set conditions, initial conditions that are far from your basin of attraction, and then you fall inside. And then you start to do a dynamics, because remember that here the colors is time, that is going around this object, but the colors are mixing up, right? So basically, if you are here, you see that you go once when the color is blue, another time when the color is red, and so on and so forth. So what does it mean? That this is a prototypical system for the chaotic system that we have seen in the atmosphere. You have recurrences, but they're not at exact time. And you have a structure that doesn't repeat exactly in the same way. And another thing that it's very important is that if I start with 2 conditions that are nearby, at a certain point, they will separate, right? So I have a limited predictability for this system. So for this system, we can start to ask the same questions that are in the weather, but I can compute this system very easily, and I know the attractor. So I can test my ideas here, and that's what I will show you for the next couple of minutes for this first part, right? So let's say that the Lorentz system has the same properties of the weather in terms of chaoticity and recurrences of state. And so for this system, I want to devise 2 metrics that will answer to this question. How rare is an observation? How long it takes to be close to this observation again? How long do we stay around the state zeta if we reach this state, right? So imagine that zeta is hurricane Helen, and this is exactly what I will have at the end of the talk. Can I answer this question using this idea of analogues and dynamical system theory? Okay, so let's start. The other things that I want to say that is written here, and I was skipping, but it's good to have the slides because you cannot, you have a reminder, is that with respect to the statistical theory, let's also go back at the introduction that Manu did for me. I don't care if a state is big or small. For me, what is interesting in dynamical system theory is that the state is rare. And I give you 2 examples, here and here. these states, the center of the wings of the attractor, this is also called the Lorentz butterfly, because it looks like a butterfly. These two states are not extremes, are not maxima or x, y, or z variable. They are somewhere in between, but they are extremes in the sense that they are rare. I cannot reach this point because they are unstable fixed point. And you see that these are the points, if we take, they are sort of the sun for the Lorentz system. So if I put a sun here, and then I put a sort of a repelling sun here, what I will get is that I have a motion around this point, a motion around this point, and then when I'm around the origin, I cannot get there, I'm diverted either in one or the other direction, okay? So, like in the solar system, we have the sun and then things go around, is a fixed point for the system, is a point that concentrates the gravity. For the Lorentz system, we have these 3 points that we cannot identify as stars, but they are there mathematically. And then the dynamics, they have to either spiral around or diverge, okay? These are the fixed point of the attractor. And they're what they regulate the dynamic of all the other points, okay? So that's the idea. So they are not maxima or minima, but they are extreme in some sense. Not only they are extremes in the sense that we cannot reach them, but they govern the dynamics of the neighboring point. You see that if I'm around here, it looks very much blue in the sense that I'm spiraling around for a long time. Okay, so their influence is felt even far from their position. And that's what we want to use, okay? So it's a different way of thinking to extremes than what is proposed by the probability distribution, because in probability the extremes are maxima or minima. So let's try to link the two things. So, and the idea is that we can link the two things if we, instead of computing maxima or minima of the variable x, y, z, we fix to compute the minima of the distances with respect to a state, right? So what I'm interested in is to understand if an observation zeta is rare or not. So the probability distribution that I'm interested in is the probability that the distance between the trajectory that I define as x vector of t and zeta is smaller than a certain radius q, okay? So I define a radius on the attractor, and I take as analogues or recurrences all the states that get close to zeta. And this I know that can happen at different time. So I try to put here the schematics. We can have a part of the trajectory that enters, for example, at time 2 and time 3. Then I have to wait 224 iterations. Then I have to wait 1,000 iterations, but I will come back at a certain point, okay? And why I will come back? But that comes from a very old theory that is made in the same building where I have the luck of teaching now, like it's in Paris, by Henri Poincaré. And it's the Poincaré recurrence theorem that basically is a guarantee that, yes, we will come back if the system is stationary and so on and so forth. Okay, so we will use this. So bear with me, there will not be mathematics or probability, but just 2 or 3 slides to understand what we are doing, okay? So now let me rename the trajectories as fm of x. This means just that every m time, so I'm iterating my system by m. M is time, okay? I will compute then I have to compute the distances between the dynamics, fm of x, and the point zeta. And I say that I want the minima of this. But is this a good observable? Remember that for the weather, what I show you is pressure and geopotential height. And why I've taken this? because the physics tell me that these are good observable of the weather. But if I look at recurrences in chaotic system, Poincaré tells me that the rate of recurrences is exponential with the distance, okay? So to get close to a point zeta, it's exponentially more difficult, okay, the closer I want to get. It's not linear. Do you know other things that work like this? Yes, for example, the scale for the earthquakes is a logarithmic scale, the Richter scale of magnitudes of earthquake. But if you like, as me, electronic music, you know also another scale that works like this is the scale for our ears that is in decibel, okay? So some natural phenomena is not scaling linearly, is scaling exponentially. And this is the case for the recurrences. So following Poincaré, I put a logarithm weight here that will allow me to look at, in principle, the minima of the logarithm of the distances, blah, blah, blah. But in fact, I also put a minus. And why I put this minus? Because I want to look not at the minima, but at the maxima. Why? Because the extreme value theory is classically done for the maxima. If you want to do it for the minima, you have to put minus. Okay? Is it clear up to here? So I repeat it once more, and for the last time. We move from the idea that extremes are maxima or minima of a variable to the idea that extremes are recurrences around the point zeta. To sample the recurrences, in principle, I have to look at the probability of entrance of a ball around the point zeta. This will be equivalent to look at the minima of the distances between the trajectory and the point. But I transform this in the maxima of this observable and put a logarithmic weight because Poincaré has already done the theorem for me. And then I can apply extreme value theory as it is. And but I know the properties of this object because there has been a lot of work in dynamical system theory for chaotic system. And so I know that the probability then that xm, our observable that I've just defined, minus the logarithm of the distances between the trajectory, is larger than u, that corresponds now to the entrance in the ball, is nothing but an exponential law. End of the story. And why I know this? Because it's a theorem that has been proved, and this corresponds to the exponential member of the generalized Pareto distribution. So this is in, well, there will be a reference at the end, but this is the work that I've done together with the mathematicians when I was doing the PhD thesis that is already more than 10 years ago. And the people who discovered the link between rarity of recurrences and extreme value theory are a Portuguese couple. So it's a love story. And basically, she is an expert of extreme value theory, and he is an expert of dynamical system theory. And that's sometimes how you discover things. But then they have the theorem, the first theorem, and then what I've done is to understand if this was really applicable to problems such as the weather and the climate, okay? And that's what will come next. So can we make mathematics useful for physics? That was the idea of my PhD thesis back in the time. And I hope to convince you that it is. The first things that we observed is that once we have this distribution that is very simple, is an exponential, right? We have only one parameter, 2 if it's a stretch exponential. In fact, we have 2. But let's think now that we have 1 in the exponential is just lambda. And lambda is, for those of you who knows the probability theory, at the same time, the location parameter and also the scale parameter of this distribution, which means the parameter of centrality, the mean for our purpose, and the standard deviation. Good. So, but what is the standard deviation here? Well, if I do 1 over this, and I remember that I've done the logarithm transformation, again, I can use Poincaré. and other theorems that came that tell me that in this way I can measure the dimension of the ball around the point zeta. What is this dimension? Well, the dimension is just the way I'm filling the space around the point, right? Imagine, and I have this here. So the dimension is 1 over the average, because this is as simple as an average of this observable xm minus u. Then I have to subtract the threshold. Are you following me up to here, or you are lost? If I lost, I can repeat once again. But basically, if I'm sampling the probability of this ball, and this is as simple as an exponential distribution, there is only one parameter, and this parameter is the dimension. Okay? But the dimension, what does it tell me? Well, now let's forget about Lorentz. Let's take me as a dynamical system, okay? So you don't know my equations. You can just track my position, and I move in a three-dimensional space. Well, first of all, you will observe that I move actually in a two-dimensional space because I cannot fly, okay? So my dimension, if you track me, okay, and you do this game, will be varying between 1 and 2, okay? When it will be 1, imagine that I'm in a corridor. I can just go straight and come back. So every time I go through the corridor, you will see a line. So if you apply the technique, well, the dimension will be 1. But what was it telling me, this dimension? Well, there is a link with the predictability. Because if I have only 1 degree of freedom, the dimension is 1, the corridor, for an observer, for you, you can tell me like, but it's just going straight, or it can come back. There is no other things that can do. Imagine now that I enter in a room like this one, okay? So I acquire 1 more degrees of freedom. So I can now move in a two-dimensional space. Imagine now I enter, so the dimension you will sample is probably 2. But if we will be like in a theater where there are rows, okay, I cannot go anywhere, I can sit. So the structure will be something that is between 1 and 2. Can be that the dimension is not integer if there are areas that are forbidden in a two-dimensional space. Okay, so the idea is that depending on the state that we are visiting, the geometry of the space, we have different dimensions. But these different dimensions, they correspond to different predictabilities because they give me some kind of structure in my dynamics, okay? So that's what I can compute and here there is a link also with the topology, okay? There is another field of mathematics that is very fascinating, that is topology. And we can think also at the topological structure of the things, like a corridor, right? If I fold it, becomes a circle, okay? But it's still a corridor, it's a circular corridor. It's a ring. And then these things can be seen as a structure that has a certain topological properties, okay? So we are exploring also the link between the dimension and topology. And for this, I have I'm working with some mathematician. But so let's go back to the Lorentz attractor, because the question is, can I compute this dimension? And the answer is yes. I can give you the code, or you can find it in my MATLAB package that there is also Python and R version, okay? Basically, what I can do is write 5 lines of code to compute this dimension. So for those of you who worked in dynamical system theory in the 80s, in the 90s, there were other techniques to estimate the dimension of a dynamical system, but they were very long in terms of and very expensive in terms of computational power, because the idea, they were based on fractioning the Lorentz attractor into small boxes and to look at the densities in each of the boxes and then to refine this and to find the scaling law. But here, using dynamical system theory, I can get rid of all this problem because I know from the work of Poincaré and my colleagues, what is the asymptotic distribution that I'm aiming for, and it's just an exponential, right? And then I know that estimating the dimension is as simple as computing the average of those exceedances. Where is the trick? The trick is that this threshold U should be large enough, where large enough is something that in extreme value theory, we have to see case by case if it's large enough or not. But we have statistical way of testing it, and it's as simple as just, and the other thing is that, sorry, I'm saying it is now, that whatever my dimension of the phase space is, I can live in 100,000 dimensional space. This will be 1D, okay? Because I'm computing the distances between, can be a big matrix and my state, but at the end, the final output will be a time series, the time series of the distances between my state and all the other state in my trajectory. So it's just as simple as a univariate fit. Yes? Yeah, sure, please feel free to interrupt, yeah.
These approach, distances are independent. They correlate.
The distances are correlated because we are in a dynamical system, but we apply, and I enter specifically in the conditions of the theorem, the two conditions that have been done by Ledbetter that guarantees that even if there is a short time correlation that is given by the dynamics, at the long range, the chaos make the trajectories forgive about these initial conditions, which means that we are still in the right conditions to apply this theory. But there is another thing, since these conditions are important only if I use one of the two approaches, that is the generalized extreme value distribution approach. When I use this generalized Pareto distribution approach, I can have clusters. I can enter in the balls and stay there, and so I can even release this constraint of independence. In fact, the proof is if you take the dynamics of the Lorentz attractor, you fix a point zeta, and you reshuffle as you want the time series, you can also make an ordering from the smallest to the largest, and you do this fit, you get the same dimension. So the dimension is insensitive to the dynamics, but of course it's produced by the dynamics, right? So if you have a structure on the attractor, the structure is produced by the dynamics, but then you can forget about how you obtain this. You just have the geometry, and that's what you get from the dimension. Yes?
To answer this question, the choice of U basically does that for you, right?
Yeah. So in fact, in this theory, you just have to choose U, and then you can test for different U's how things change. And of course, many of the discussions that we had with the mathematician were that when you look at the results for the Lorentz attractor, so now what I'm plotting here, it's not the colors is not time anymore, it's the value of the dimension. So for each point zeta in alternative, I'm computing the dimension. So I'm making zeta each different point, and I can get a clue of what is the dimension. And here the scale is saturated by 3, but in principle, since I'm not saying to the technique that the system is living in a three-dimensional space, I can get higher values, which is also the case here. And we will come back to this. But the interesting thing is that in most of the region of the attractor, I get dimension 2, something that is around 2. If I take the average of all the points, I get 2.06, which is consistent with the classical estimate that are done with the box counting, but I get more. I get that for each point, I have an idea of what is the dimension around the point. And things are interesting because near the fixed point, near the wings here, if I try to sample them, I have a dimension that is very low. Of course, because in this dynamics, I can just spiral around, okay? Remember the example of the corridor. It's a very simple dynamic. Then there is an area where the dimension is high, here, here, and here. This is the area where I can have divergence, because Here, I go out from the dynamic of the fixed point to the dynamics of the wings. And here is the landing part where I can go to these wings or somewhere again in the middle. And these are also an area of high uncertainty for the trajectories, okay? And then there are the outer part of the attractor, the states that are rare. I can go outside. This is also areas where the dimension is higher, but because my points, my recurrence points are far away. So the mathematicians will say like, no. And that's the discussion that we had for a few years with the colleagues in dynamical systems. No, you should get always 2.26 except for a set of measured 0. So except for these 3 points where you should get another value. And then we thought a lot about this and we said like, yes, but if you look at the dynamics here, if you look at the movie of the Lorentz attractor, you feel the presence of the unstable fixed point. So if you observe your system for a finite time, your dynamic will be influenced by that fixed point around there. So here, there is an important point of this theory, that this theory is useful when you want to make sense of it for a certain time scales, right? Imagine that you are an alien, that you live at a super fast speed, and for you, the human days don't count, right? You see all the weather as a very accelerated movie, and you are very resistant. You are like the Death Stars, if you've seen Star Wars, right? You are like a Death Stars, you are there, and you don't feel storms and whatever. You live a very long time, you don't care about the storms and so on. But if you're a human being and your time scale is 60, 100, 120 years, okay, then you care about this time scale. And then it will make sense for you that the dimension is different at that point. Saying another way, if I iterate this system for infinite time, I will get that this area where the dimension is different from 2.26 shrinks, okay? They will always be there. I will always feel the presence of unstable fixed point. But for a given time scales, I will get something that is a finite size result, but is reminiscent of the properties of the attractor that is underlying, okay? And this is what is useful for. So I say it in another way again, what is useful this is not to get the exact value of the dimension, but it is very useful to compare states from this, for example, area to this area, and to get what is larger and what is smaller, okay? And this is what we will use. But there is another thing that, yes.
One more question. If you could go back to slide where your equation is still there, I want to bring it back to. So one challenge that appears to me on this as we go to high dimensions, because you mentioned that, and that's why this question is prompted, is that the distance calculation becomes the problem. What is our distance metric that actually decomposes the high dimension model, right?
Yeah, so we had sure. We had a paper on this by the postdoctoral researcher Flavio Pons, and we can the good thing is that we can compute and adjust for these curves of dimensionality in this theory. And in fact, we can understand, for example, in the climate data that I will show again very soon, if our system is, if we are sampling a low dimensional properties or we are just sampling the curves of dimensionality. So we can adjust for that.
So I'll discuss with you later one trick I've been using for this.
Thanks. Yeah.
Previous slides we find the distance. Previous one. The test of follow then is for here you define the circle in the Euclidean space and the contractor of the state points in the fractal 2 points or something embedded in the 3-dimensional space. So the object itself is manifold.
Yes. Yeah.
Doesn't it more aesthetically elegantly beautify the space based on the manifold?
Yes. Thank you for your questions. This is also something that with the mathematician we discuss a lot. You can do this theory for cylinders that are the most appropriate things, cylinders, because you have a direction of the motion. It doesn't change much for the practical purpose again. So you have to imagine this for the way I will use it in physics as a sort of lens, something that for me, it's a way to investigating the attractor, okay? And the thing is that it's like an instrument, and if I apply this instrument to all the states of my attractor, I can look at some differences between the different states. Of course, I can refine the instrument to make it more powerful for some specific dynamics or not. And we have many, many papers on this, how to change the observable, how to change the many different things. But most of the things I will say, they are independent on these issues that we have evaluated. More questions on this? So I will go, thanks for your questions. I will go now to another indicators that will depend on the dynamics. And this is an indicator of persistence. This is very simple. Once I enter in the ball, how long do I stay? Okay, and to compute this, there is again a quantity that is the extremal index in extreme value theory, that is a measure of clustering, and it is just 1 over the typical cluster size of my recurrences here, okay? So in this case, my extremal index theta will be 1/2, 1 over 2, because every cluster is of length 2. For this, I need the time dependence, but it's very useful because again, there is a link between the persistence and the predictability, of course, right? Because you see this in the desert, it's very hard for you to beat the weather forecast that tomorrow it's gonna be sunny again, no? And that's persistence. So persistence is predictability, and I can construct this extremal index, and I can measure the extremal index with respect to the dynamics. Again, you see that this figure is different than the dimension, right? And what you can see is that there are 3 points where the extremal index is low, that corresponds to the 3 unstable fixed points of the dynamics, the sum of the Lorentz attractor. And the idea is that the dynamics, when I get, so the dynamics is like this. I go to the wings and the extremal index is high, which means that I have low clustering. So this is fast. Then I go here, I slow down, then it's fast again, fast, slow down. And when I get to the close to the center of the wings, I spiral and I stay a long time. Then I go again, fast away, and so on and so forth. That's what the extremal index is telling me. So it's different than the dimension. Look, this point here. The dimension, I don't see much. But in the extremal index, yes. So the 2 informations are complementary. And they give me different things. Remember that the extremal index is a frequency. So it depends on the time I'm using to sample the system. It's a clock, sort of a clock, right? So it's also telling me whether I'm using the right time scale, or it's telling me the time scale of the phenomena that I want to address in the system, right? Okay, so that's for the 2 indicators for the Lorentz 1963. And now after this almost 1 hour of like saying, okay, thank you, but now what do we do with this? We go back to the weather data, and I will show you that we can apply exactly the same 5-line codes that will just compute the distances between state and the data, then compute the logarithm, and then just look at the average of the exceedances that we give you the dimension to understand how rare, how recurrent, and how persistent, how predictable are atmospheric state. So this is what I get if I look at this domain, that is the North Atlantic, again, the domain that you have seen before. And the only thing here, I don't have the attractor, right? So I don't have like Lorentz, X, Y, Z, and I cannot plot the dimension and the persistence on the attractor. But one thing that I can do, I can plot the dimension versus the persistence for each daily map. And so each point will be the value of dimension and persistence for a daily map. Sorry, I have to take a tissue. And well, I can take it perhaps from there. And what I will do with this dimension and persistence is that I can look at the states that are maxima of the dimension, maxima of the dimension will be here, maxima of the persistence that will be low theta index, minima of the dimension, and maxima of the persistence, right? Sorry. And what I will see is that what I can do is take conditional averages, composites of the days that are, for example, the 5% higher dimension, 5% lower dimension, higher persistence, low persistence. And guess what we get? We didn't know this before we did it, but we get the weather regimes. So the typical states of the weather that we can that are atypical in some sense, because here we have extremes and here the anomalies are strong. We talk about 10 hectopascal, which is not negligible, but somehow we can separate the phase space in typical patterns. And I don't know how well you are familiar with the dynamics at mid-latitude, but let's take this one. That is the state with low dimension. This is a North Atlantic oscillation positive pattern that is consisting of low pressure to the north and high pressure to the south. Well, that looks like the most reasonable pattern to have in the North Atlantic. And in fact, is the one that has the lowest complexity, the lowest dimension, right? Another pattern that the one with the highest dimension is the messed up blocking pattern, right? Where we have not a zonal structure, high, low, but low, low, high, okay? This is it's not a state that the system likes in terms of predictability. In fact, it has high dimension. And we can define ridges and North Atlantic oscillation minus as extremes of persistence. And you can see that if we just take the NAO index, it cannot give us the same richness of state as this dimension persistent analysis, okay? So we can use these indicators to determine that this is rarer and less predictable than this, that is the most predictable and low dimension. This is the most the least persistent, and this is the most persistent state. And the time scale, it's 2-3 days. That is what we expect for the dynamics at mid-latitude. You can repeat the experiment with the sea surface temperature, the ocean, and you get that this value typically is 0.02, that is a time scale of 2 weeks. So this is reasonable. Another thing that we can do is, since we have a value of the dimension for every day, we can look at the time series, right? And what we see from the time series is that we have a variability. We have cycles, seasonal, like annual cycle, and that most of the extremes for the pressure happen in winter, where we can go from states that are low dimensional, that are NAO plus, to states that are high dimensional and are the blocking. So we have this sharp transition. Another thing that we can see is that the value are between 5 and 25. So what does it mean? It means that the number of objects, low pressure and high pressure system that we can fit in this space are typically of this order. So if you take, this is was for the NCEP pre-analysis. What we did is that we tried ERA 5, that is 8 times more resolved. The value do not change. Then a colleague in Bonn, Petra Friedrichs, she said, like, I don't believe that the computation you're doing is right. So she took a very long climate simulation, 2,000 years, and she found the same result. Okay, so this is what we get. And then what is useful for is to link real extremes with, for example, things that happen in the media. So extremes as we have it in the media. And so what I did in this paper is that I took the Wikipedia page, European windstorms, and then I look whether there was an identity, well, correspondence between a certain area of my dimension persistent diagram and the occurrence of the storm. And in fact, you find that most of the named storm for Europe, they are in this area. So they correspond to minima of the dimension. Okay, so that's the kind of things that you can do. So that's the first things, and I don't know why this doesn't work. But then another thing that we did last year, okay, is like, can we use this idea of recurrences now? Let's go to non-stationary, okay? We have climate change. Can we use the idea of getting the recurrences to understand if there is a climate change signal in the atmospheric circulation? And this is a long-standing problem, right? Because the thing is, we know that there is, we know very well that there is a relationship between CO2 increase and temperature increase, but the circulation at mid-latitude depends not on the global temperature, but the temperature differences between tropics and the poles, which is non-uniform through continents, through the oceans, and is affected by lots of variability. Okay, so how we can do? We can take, again, we do the analysis for each daily map from 1950 to today, but this time we look at how many recurrences we have. So we fix the number of recurrences of analogues that we want to get. Okay, so we fix a quantile for our statistics. And then we see, we fit a trend in decades, okay? So we see if we have more recurrences now than before, and vice versa. So somehow we want to analyze which patterns are becoming more frequent in terms of recurrences and which patterns are becoming less frequent. What is we expect more and what we expect less. And okay, then I will go with the arrows. So we can do this in a robust way. So the things that we tried is like define a ball that is a certain size, then shrink again 2 times, and only consider the days for which there was a positive trend in the number of recurrences, which means days that become more frequent. For the 3 quantiles, this was a pass, okay, and we took these days, and then do the same for the days that were becoming less frequent, okay, and we separate, of course, winter and summer. So the days that have increasing trends in winter are the days that looks like this. So this is with low pressure anomalies here and high pressure anomalies in the southern part of the domain. So this is associated with windier extremes, so more storms in the north of Europe. But the bad news for me is also that the Mediterranean is not receiving anymore the cyclones that are brought by the low pressure system, okay, and so droughts, okay, we have tendency to get more droughts. And the decreasing trend is not it's not, you see that there is not symmetry here. I wouldn't say that there is a symmetry. It's a pattern that is some characteristic that is more meridional, where there is a low pressure here and a high pressure here. This is disappearing. This is for winter. And then for summer, we have also a signal of, again, it's lower because the signal in pressure is, there are less pressure contrasts, but it's significant. So we have that this low pressure is increasing here, but this push warm and wet air towards Spain and France. So we have thunderstorm, and the Mediterranean is still dry. This is increasing, and then decreasing is the one that has, so it's increasing also the temperature. This is, I show temperature here. And the patterns that bring fresh weather in Europe are decreasing. So bad news. Then we can link, this is what we have already, I'm not projecting, this is detected changes, the days that are becoming more frequent. And then the other things is that we can link the impacts of this pattern to heat waves in summer and in winter to windstorm. So here I've taken the number of deaths is the size of the ball during the heat waves. And where there is a violet, it means that corresponds to day for which the circulation is becoming more frequent. Where there is blue, there is negative or no trends, and then not assigned is then when I have just one day that belongs, one day of all the heat wave that belongs to this or other case. So, but you see that most of the days where we have recorded deaths from heat wave in Europe, they are associated with this changing pattern that are becoming more frequent. Yes? Yeah.
How many current analogues, civil engineers, so I don't know much, but I've been fighting some colleagues about this. Statistical analysis and this idea of hard exponent, long-term climate. How does this result account for that? So the persistence of an annual scale.
Yeah. We have tried.
So these are going up, okay, but are they going to go down if we have other 100 years?
Yeah, so what the things that we tried to, of course, we got these questions by the reviewers, and the things that we tried is like double the time in back in the past, so start from the beginning of 20th century, and we see these trends. Then do a different parts of the period, so this starts in 1950, if we start in 1980, we still have the trend. So we try different periods, and this is a very robust signal. Also, the size of the anomaly is huge. And the thing is problematic is that what happens in the future, right? So as you say, if we extrapolate the trend linearly, at a certain point, we have that all the day looks like the day that are increasing, which doesn't make much sense. The problem is the climate models, and for this we have 2 papers already published, they do not reproduce these trends, not even by chance. So we would in the historical period, and that's the big issue, is that we don't even have the 5% of the climate, the model that even for the wrong reason should reproduce this, they are not there. So that's very worrying. And was one of the reasons for the paper to be rejected in Nature Climate Change, because the editor decision was like, since the models since you don't find the same signal in the models on the observation, is not worth publication. Then we submitted to PNAS, and Kerry Emmanuel was the editor, and he said, no, this guy should get this published, and I override what one of the reviewers that had this comment, because it means that there is a problem either in the observation or in the model. But the observation are the signal is very robust. And we have another paper with Robert Vautard that see that the model do not reproduce the warming for Western Europe. So it's worrying. So we have this signal, and this signal is robust in the observation, but we cannot confirm it in the model, which means that our hypothesis is that the models do not have the right feedback between ocean, land, ocean, poles that should be driving these dynamics. I can cite other literature, but we can discuss. The other things.
Actually, just on that point, I've done a number of analyses, not bothered to publish them, but if you look at the reanalysis models, atmospheric circulation, and the pre-run models for the 20th century, there is complete disconnect. So, it's not surprising that what you're.
So, and the other things that we can do is to link this, for example, to the modes of variability. Can we explain this trend if you look at the Atlantic multi-decadal oscillation, Pacific decadal oscillation? No, they cannot explain alone. And there is another paper now that we have done for the Indo-Pacific region, the one I was mentioning this morning, that show also that for the Indo-Pacific, we are polarizing the climate on few states that are either very dry or very wet. And this is also worrying because no models can reproduce the signal. So we are in an unknown territory, but this is what we observe in terms of changes already observed. And they make sense. So another thing that I want to stress is that this pattern here with the low here and then high here, we see this keeping happening in in the current summers, in the summers in Europe. And we have another paper that we called with Fabio D'Andrea of LMD, the Xanax paper, the deep depression paper. we had the Xanax icon there because we see that these, in fact, even if we use other methodologies, they are becoming increasingly more frequent, which means lots of it for Europe. I also did the analysis for the North American continent. I never have the time to publish it, but there are also patterns that are becoming increasingly more frequent in US and North America and other that are disappearing. The signal is less clear than for the North Atlantic for some, and is coherent with the fact, for example, that we have, well, the area of the eastern United States where still the signal of increasing the heat wave is not very clear. So we can find back things that are already present in the IPCC literature and so on and so forth. But this is a warning signal for Europe. And now the last part, I'm on time, it's attribution, right? Of course, for the moment, I've shown you aggregated statistics. I did composites, okay? But in principle, I have for each single state, for each single day, my statistics. So I'm gonna use this dynamical system theory to do attribution. Attribution is the process of determining the cause of observed changes in extreme events, right? And it's like baking cakes. Okay, so what does it mean, this? So imagine that Upmanu is a very good friend of mine, and he offered me a chocolate cake, but I become vegan, and I cannot eat butter, okay? But Upmanu lives, and I don't have the time to ask him if there was butter or not in the cake, okay? Butter is the equivalent of anthropogenic climate change, and the cake is an extreme event, okay? So what I can do is that I have two strategies. A strategy, if I'm very rich, I can bake many cakes with and without butters, and then see if Upmanu's cake resembles more the cake with or without butter, okay? Or I have a long record, obviously, since we are friends, Upmanu offered me several cakes, and I can see if in time there was a change in the structure of the cake, in the ingredients, okay? So it's a difficult problem, right? And here you see, for example, that I have many other things that even if I have two kitchens and I can produce many cake, can give me different results. First, the cook, the scientist that analyze the data. We can make error, false positive, false negative, because we see climate change and we have the tendency to say like, yes, there is a change in this. So then the kitchen, the climate models I'm using, and an example was the study that I was mentioning before. Are the models adapt to do attribution? And then I have other ingredients. They are ENSO, El Niño, La Niña, the blocking, the volcanoes, ocean temperature. Okay, so there are many things that can go wrong when I do attribution. And the idea is that we built a climameter that is a framework that uses all this dynamical system theory to make rapid attribution. And now we have over 25 institutions. And for the US, we have Columbia with the colleagues Susana Camargo. She's participating. And we have also the NOAA. And we have realized in 1 year 60 studies of attribution studies using this dynamical system framework. And since what we will use, you have understood already, is the cheap option, that is we love climate models, but we see that they're not very adapted to studying weather extremes. So what we use is the past data. And the idea is that we have already enough data to have recurrences and to divide, and we have enough changes. And the idea is that we can divide these data into two periods, past and present period, less and more affected with climate change and look how analogues of certain weather phenomena have changes in the two periods. I can do it in 10 minutes because with the first part done, you have this very clear. And then, if you go on the Climameter webpage, you will see that we have a dashboard. We can look at the sources of detected changes. And we didn't know this before starting, right? But only 3 or 4 events are in green, which means that they are only influenced by natural variability. Then the rest is mostly red and orange. So there is a clear signal of anthropogenic climate change. Not surprising. We start in 2023. The other things that we can say with the analogues is that is our event unique in terms of analogues? It's the first time that we see it happening. Of course, if it's unique, then the confidence in the attribution statement is low because we don't have analogues. And if it's a common event, then our confidence is high. Okay? So that's all the kind of output that we give. But I will show you how it works just with one example. So first of all, attribution, we don't want to attribute all the events. We want to attribute only events that have an impact. So we start from here. What happened, like for example, with Hurricane Helene, many things, many impact on all these indicators. So then the trigger is, we see it in the news, or our communication team tell us, hey, Davide, can you do the attribution for Hurricane Helene? And we say like, what happened? Yes, we are going to do the attribution. And then what were the hazards? Well, we had rain, we had heat, we had rain and wind, for example, for the hurricane, right? But what was the cause? Well, the cause was a cyclone, okay? So what is done normally, and then for cyclone, we have to understand if it's been modified by greenhouse gases emission or climate variability. So normally attribution, the classical statistical attribution was based on extreme value theory and was at this level, the level of the hazard. But with the analogues, you have understood, I'm tracking the dynamic. So I'm tracking the cyclones. So it means that we can do, in Climameter, we are at this level, and we track multiple hazards with the same object. So the way it works is what I told you. So we use reanalysis, and we use MSWX. You know, this reanalysis is based on ERA 5, but it adds, for the last days, the weather forecasts. And it's very easy to download. It's as simple as synchronizing a Google folder. So it's like a paradise. You just have an rsync command in your script, and you have the data. And then the event definition is again a pressure map of a certain region that contains the event. And then we look at analogues in the past and in the present period, and we do simply present minus past. The present being the analogues in the second part of the period. So for us, this will be 2001, 2023, minus the analogues of the past, that are 1979, 2000. Then we diagnose changes in pressure, temperature, precipitation, and winds, and we exclude the modes of variability. The example, Hurricane Helene, I don't think I have to say much about this because, you know, it's been a total disaster, okay? And the things that we want to see is how climate change has modified this. So here it's how we proceed. This column is the event, okay? So this is the pressure map of Hurricane Helene, and we select this region. So what I look is all the other maps in the database, and I look for the 15 best analogues in the past and in the present. Okay, I do it only for the pressure, and then I take difference, present minus past. And as you can see, there is not much of a difference. And first of all, the things that you see is that the analogues are not good. So they do not resemble the target. Okay, and then if I take differences, there is no statistical significant difference. How I do statistical significance? I mix the dates between the two periods, and I do bootstrap. So I select different time. Temperature, there is an increase in temperature in the coast. So the diagnosed changes are not analogues of temperature, precipitation. The analogues are only for the pressure, because I'm looking at the weather phenomenon causing this hazard, okay? So difference in pressure, yes, on the coast, huge difference in precipitation in this area that has been flooded, and then also significant differences in wind of order of 10 kilometers, okay? So that's the analysis. And then we have all the dynamical system metrics. So you know violin plots? It's like box plots, right? This rose color is for the present period, and this is for the past period. What we can define is an index of quality of the analogues that tells me how good are the analogues that I'm measuring. This will be the distance from the event from the analogues. Imagine that I'm the event. In this case, I'm far from you, but you are close to each other. So me, I'm the blue point, is the distance from me to you, and the violin is the distance between you, okay? So this point is out of the distribution for both the past period and the present period. So my quality is low confidence, okay? Then I have the dimension and the persistence. I can see if there is a change. And of course, I can compute statistics. I can also look at when they happen in terms of season, the analogues in the past and in the present. And then other things that I can see if there is a shift in the modes of variability during the dates of the analogues, okay? If there is no shift, it means that the analogues occur with the same phase of the ENSO, of the AMO, or the PDO, that are the three modes that we analyze for the two periods. So I can exclude that there is a role of these modes of variability for this event. But here I cannot exclude that there is a role of the AMO and of the PDO because I have a significant shift. And then I can fit frequency trend, but this we don't use for the analysis because we are, and this goes back to this, your question, to a short period here, 1979 to present. Okay, and so then with this indicator, we construct what we give to the press, that is this one, these 2 meters. So this is pointing to red when we have no modes of variability that can influence the event. And then we have the matrix of uniqueness, okay? So this is what we say, is that then there is a first part that comments on the changes in terms of precipitation and wind. So we say cyclones similar to Hurricane Helene are up to 7 millimeters per day, up to 20% wetter in Southeast United States, and up to 7 kilometers winders in Florida's Gulf in the present and they have been in the past. Then we have the assessment of the uniqueness, and then we say that natural climate variability may have played a role, okay? And that's what we give to the press. And that's the figure that you find if you go in the climate meter, that is a synthetic figures of what I've already shown. But the thing is that here the event is the first row, okay? And here the changes are second row. And we can pick up cities to see what are the changes in the cities. That is information relevant for the stakeholders. And here we have Charlotte, Atlanta, and Knoxville, where we have significant increase in precipitation, is the blue bar, and also in wind for all the cities. And that's what we give to the press. And then what we get is that we have, there are not the icons, but for example, this was picked up by USA Today, The Independent, NBC News, CNN, and this is out really what goes in the press. The Wall Street Journal, I didn't put all of them. We had more than 1,000 articles citing this study, which is a huge impact, okay? And all of this is just possible with dynamical system theory, because the analysis that we do in the climate meter, it runs on my laptop that is here. So it's very low emission technique in terms of, and it's very honest in the sense that in the study, there is low confidence because we don't have analogues. And the fact that we link to the meteorology allow us to write a story about. It's not just statistical changes. We have the support of the physics. We say like this storm has been more, have produced more rainfall because we saw a warming of the temperature. Okay, so more moist heat, and more precipitation, more wind, more advection. So we can tell a story. So if you're interested in joining Climate Meter, as you have understood, is a consortium of scientists. It can be just as simple as saying like, hey, Davide, this happened in Arizona. Can you do an attribution study about this? And then we decide. And you can also participate in writing the events. You can be in the core team and so on and so forth. And that's all, except that there are now two, I want to stress that there are, you know, perhaps the World Weather Attribution that is doing attribution studies with statistical methodology, but they have an interesting part that is the exposure and vulnerability that we don't have because we are in the meteorological part, okay? So we are complementary. And our idea is not, of course, the idea is to enhance communication on climate extremes. And there is also huge responsibility on this because, as you can see, there is a lot of going on about this rapid communication. But still, these reports, they cannot substitute peer-reviewed studies. So we have many peer-reviewed studies that use this methodology and that are used. Now we're also doing one on hydrological analogues with colleagues in the UK. And I finish, well, I already gave the messages, but the idea is that dynamical system can be very useful for all of this chain that allow to classify event not by their magnitude, but by their rarity. And we can get trends, but we can also get single event output. And so, yeah, there is a lot left to do, which is including, of course, dynamical system is very flexible. So we can go to impact models, we can go to other variables, hydrology, and there are many things that we can do about this. And here is some references, but the best way, I think I will give you the slides if you want, and the talk is recorded. You can flash the QR code and get all of them from my website or just drop me an email if you want. And yeah, have a look on Climate Meter. Thank you very much again for your invitation. And